Hello everyone. So let's look at the line integral, and we want to go back again to the concept of a conservative field. So you must remember, when you have a conservative field, you can find a scalar potential. So let's look at this example. So now in this case, you have a force field which is given by this equation here. And then in this case, the question asks you to first prove that this is a conservative field, right? So what should you do? If you still remember, you will know that you just have to evaluate the curl of f, and it should be equals to 0. So there is nothing special here, just brute force calculation. You will just find nabla cross with f, and this in terms of a determinants is written like this, and you will satisfy yourself that this is actually equals to 0, right? So the second part, which is slightly more tougher, is that you want to find the scalar potential in this case. So here they specifically say that you have a f equals to negative nabla phi, and phi is your scalar potential. So you want to find phi. So what should you do? Here you should try to simplify the equation, probably in the way that you put negative phi and you put this as a w, as I did here, and this one w should be equals to an integral of f dot dr. So in the next slide we will see why is this so. So we start with f equals to nabla w. So this is a starting point, and then we take a dot product with a dr, and here you have a dr on the left and the right hand side, and from there you can expand, because nabla, or the gradient, is written in this form, whereas dr is written in like this. So what you do next is simply to take the dot product between the two, and you will easily get this line, this equation. And the next part is that you will take the integration between in both sides, in both sides, and then you will see that this is the exact differential as we have seen in the previous class. And then finally your line integral, the w, is just simply the value at point B and A. So this shows that my equation, which I shown in the previous slide, w equals to integral of f dot dr. So that is one equation that you must always remember. It gives you the relationship between your scalar potential and your f, your force field. So from there, when you know your w, you will then fit back to this, and from w you will get phi. So in this question, what you want is just your phi. So let's go to the actual integration, where your f is given by this expression. So when you take f dot dr, you will have this resulting expression that you need to evaluate, right? But now we have a problem, because what is my starting point and what is my end point, right? But then this is rather easy if you remember the tips, which is in the conservative field, you have proved that this is a conservative field. The path that you take doesn't matter. So you can go from A to B to C, or you go from A to D to C, provided that the beginning and the last point is the same, your integral is going to be the same, right? So here what we can do is we can choose an easy way to do it. So we start with the origin, which is 0, 0, and then we go to the next point, which is x 0, 0. So basically you are moving in the x direction while maintaining your y and z equals to 0. So in this case, as you see, y equals to z equals to 0, but then here dy equals to dz is also equals to 0, because there is no increment in y and z. So that is the first path, and the second path is you go from x 0, 0, right? You start with this point and you go to x, y, 0. So here your dx and dz is equals to 0, because here you start with x and you end up with x, dx equals to 0, and dz you start with 0 and you end up with 0. Fine. And from the next step is to look at the dz, which is you take the path from xy 0 to xyz. So here dx you start with x, you end up with x, dx equals to 0, y, and you end up with y, and you have dy equals to 0, right? So using this this information, we will basically make the integral of this equation, right? Okay, so let's look at step number 1, that is path 1. I will go from 0, 0, 0 to x 0, 0. So I will need to evaluate the I component in my force field, right? So here I will have to evaluate this expression. dy dz is equals to 0, so I can just remove them. And here you see that my y and z is equals to 0, and therefore this term does not contribute. So then we go to the next step, which is from x 0, 0 to x y 0. And here my dx is equals to 0, my dz is equals to 0, and I only have my dy term. So in my dy term, I have this integral. So if I integrate this, I will get x squared y, right? So step 3. Step 3, we start with x, y, 0, and we go to x, y, z. So dx, dy is equals to 0. So this is my dz term. Integrated, I will get minus x, z to the power of 3, and minus z. So now the total integral will be just a sum of all these contributions. So basically my w is equals to x squared y minus xz cubed minus z. And if you remember, we define w as negative phi, and therefore my scalar potential that I want, phi, is basically, I will take the negative value of this, and this is the final answer. So that is how you find the scalar potential in the case of a force field where it is conservative. Right, so let's go to the next slide. So this is another example, a very nice example where you look at the electric field and you want to see how much work is needed in order to bring a charged particle that is far away to a point charge. So let's have a look. So so let's look at this example. Here, this is the Cartesian representation. So here you will have a charged particle which is located at R. We assume that this is a positive charge. And then you have another particle, let's say a negative charge, located at somewhere far away, so that we write the R prime, that is the location of this particle, to be infinity. And this positive charge particle is going to cause an electric field, right? So which I try to represent it in terms of this circular path. And this electric field is going to pull the negative charge particle towards it, right? So you take note of the arrow which is going inwards. So normally we can solve this equation in a Cartesian coordinate if you like, but it is much easier if you write your electric field in terms of unit vector in the r direction. So this is a unit vector in the r direction. So in Gaussian unit, the electric field is written like this, and here you have to be very careful because now you have a r squared over here, and this is a magnitude, right? And ER is a unit vector in the r direction, which is written like this one, that is r with the arrow to signify that this is a vector, whereas the r at the denominator, this is going to be a magnitude, right? So when you replace them like this, and then you will have this equation q over r to the power of 3 times the vector of r. But here, this is very important for you to remember that this r with the arrow cannot be cancelled with the r at the bottom, because this is a vector, whereas this is a magnitude. Right. So now, in the case where you want to bring the charged particle from somewhere far away towards this positive charged particle, you are going to do some work. And the work is written as the integral of the force field, which is E dot with negative dr. So here there is a negative sign because you are going to bring the particle inwards, whereas if you are just going to push it outwards, then this is going to be a positive dr. Right. So then you will replace the E, which is your electric field, into the equations, and you will have this expression. So here you have a negative which comes from this negative here, and here you are going to integrate from infinity to r. So basically you are going from here to here, and this is the same as writing it like this, where you do not have a negative sign here, but you are going from r to infinity, that is from r to here. Okay, so these are the same way of writing the equation. But here what we need to know is how to evaluate this term, so which is r dot dr, both which is a vector. So in order to look at how to do this, we will discuss it in the next slide. So in order to know how to evaluate that term, let's look at this this differentiation, where you want to differentiate r, which is a vector, dot another vector of r. So if you take the differentiation, you will see that you will get this r dot dr plus dr dot r. And since this is the same, they are scalar product, and you will have 2r dot dr. So you will have this one answer. But at the same time, you must also remember that r dot r, they will give you a magnitude of the vector. So now you have r squared. So this is a vector dot the vector, and you have a scalar. So let's look at this. If you differentiate these terms, right, you will have if you differentiate this, you will get 2r dr. And you will see that you start with the same expression, and then you have two different answers, which means that you have r, which is a vector, dot dr, that is a vector. This is equals to r, which is a magnitude, and dr, and this is a magnitude as well. Right. So if now when you know this, you can go back to the integral. So when you put this r dot dr, you replace it by this corresponding term, and you integrate them, you will get q over r. So basically this w equals to q over r is the work that you need to do in order to bring the charged particle from far away to a point in r, which is where your charged particle is, right? So before we end, I just want to show an example, not to show an example, but then to discuss about what should we, or what can we understand with this equation, right? So after some tedious derivation, this is the answer that we get. So here, if you look at this diagram, this is the charged particle that is pulling or attracting this charged particle, which is somewhere far away, right? So here you look, if this blue particle is very near to the origin, so if let's say you just bring this down all the way here, and then your r is going to be small, right, because it is very near to the origin, but then it will be very far away from this charged particle that it is attracting. So in this case, if you look at this equation, my r is going to be small and my work is going to be large. And this makes sense because now I'm very far away from this particle, so I want to attract them. I have to spend more work. So conversely, if this charged particle is very far away from the origin, let's say here, given by the red pointer here, and here my R is going to be very large, and at the end my W is going to be small because it is nearer to this charged particle, so the amount of work that I need to do is going to be small. So here you see this is the application of a line integral in physics, where I'm sure you have saw this kind of application before, right? So I hope you have managed to understand a little bit about line integral from my lectures. So basically that is all on a line integral. Please do the following 4 questions, and I will tell you when you will need to submit it after this. So basically there's the 2 questions here, number 5 and number 7. You can do this, and then the next one will be number 16 and 20. So I will ask you all to submit this 4, but I hope that you will do more than this. You can try to get those questions in the book, right? So that's all from me. So all the best. See you.